Song's first lecture was on reviewing classic mechanism design, and now I'm going to start our discussion of robust auction design. So in the first lecture, we explored various instances of the optimal auction design model, Meyerson 1981, Bulow and Klemper, and Kramer and McLean. A core component of each of these models is a description of the bidder's information. What do they know about the value of the good being sold for them? And what do they know about what others know? And all of those examples, all of those models can be viewed as containing special instances of what we call an information structure. And there's parallel terminology in game theory. An information structure is often also called a type space. Songs and I are going to favor this terminology through these lectures. Okay, so I'm going to proceed a bit more abstractly and describe a framework for information that goes beyond just the auction model, but then we'll specialize it back to the auction model. So fix a set of states of the world that I'll call big theta. And these are, think of these as payoff relevant states that affect players' preferences over outcomes, or agents' preferences over outcomes. So given this set of payoff relevant states, an information structure, which we'll denote by a curly I, consists of a pair of what we'll call sets of signals and this pi. So this S consists of a set Si of signals for each player I or agent I. And then there's a function, pi I, that maps each signal of bidder I into a distribution over S minus I and theta. So this pi I function represents bidder I's beliefs about both the payoff relevant state and what others know. Okay, so you could describe the informational assumptions in each of those models from lecture 1 as an example of an information structure. So for example, in Vickery's independent private value model, that would be a case where the payoff relevant state is the vector of all of the bidder's values for the good being sold. Each bidder's set of possible signals is equal to their set of possible values. And this belief function simply puts probability 1 on the event where everybody's signal coincides with their value, and the distribution over other signals is equal to the distribution, that prior independent distribution over others' values. Okay, so this is a special case where there's a lot of correlation between your signal and your value. Effectively, your signal is your value. Okay, so Harsanyi famously proposed that we use information structures as an analytically way to model distributed information and differential information and higher order beliefs. So rather than saying, what is an agent's belief about the state? What is an agent's belief about others' beliefs about the state and the state, et cetera, and trying to describe those sequences of belief, higher order beliefs, you could just say, what are the set of signals that an agent has, where a signal is essentially a summary of that infinite hierarchy, and describe how that's related to others' hierarchies. Okay, so basically an SI is nothing more than a shorthand notation for a particular hierarchy that actually could be derived from the SI and pi I objects if we wanted to. So Harsanyi gave somewhat informal arguments that this was a sufficiently general way to model information. Mertens and Zamir later described a sense in which this is really without loss to describe distributed information with information structures, as long as those higher order beliefs that you're trying to describe satisfy some minimal internal consistency criteria. Okay, so that's what we do in game theory and incomplete information game theory. We describe information and beliefs with information structures. There's a special class of information structures which subsumes all of the examples in lecture 1, which are information structures where beliefs can be derived from what I'll call a common prior. Okay, so for example, in the independent private value model, we could start by saying that there is a joint distribution over all of the bidders' values, in this case independent, with marginal distributions Fi, as Songza set up. And then the private value hypothesis is that your signal is equal to your value. So you learn exactly what your value is with probability 1. And the important thing is that each bidder's belief that I showed you on the previous slide could then be derived from this prior joint distribution over signals and values just by Bayesian updating. Say, let me start with that prior condition on the fact that I got a signal Si, and then my beliefs will be exactly F minus I. Okay. More broadly, we could say that a pi that's a big distribution over everybody's signals and the payoff relevant state is a common prior for an information structure if these beliefs that each signal has are obtained by Bayesian updating from that prior. Okay. And the common prior assumption is simply that the information structure has a common prior. Okay. Now, all of those examples that Songzi was describing have a common prior. In fact, it's not just that the bidders have a common prior, it's also that the seller shares that common prior, and the seller's beliefs about what the bidders' values and types are also derived from that prior. And this assumption is somewhat controversial, even though it is ubiquitous, especially in applied game theory. I'm not going to go into detail in this lecture on the pros and cons of and philosophical arguments for and against the common prior assumption. I think, at the end of the day, why is it used so much in applied game theory is largely because of tractability. And, it provides this integrated way of viewing all of the agent's welfare from an ex-ante point of view that lets us solve for optimal mechanisms, welfare maximizing mechanisms, et cetera. Okay. So circling back in a little more detail to the models from lecture 1, we've made a lot of strong assumptions. Those classical models make a lot of strong assumptions about what is common knowledge among the bidders and the mechanism designer. So first of all, common priors from which all of the bidders' beliefs are derived, common knowledge of the rules of the auction mechanism that's being played, also common knowledge that a particular strategy profile is being played where, in the case of direct mechanisms, all of the bidders are truthfully reporting their types. In an applied setting, it really strains credulity that that economic agents would agree exactly on all of these things. Okay, and on top of all of that, we've assumed very stylized and simplistic forms for information that, in particular, private values. We've assumed independence of the values and therefore independence of the signals. Often there are extra symmetry and regularity assumptions that are used in characterizing optimal mechanisms. So, there's no reason to think that all of these properties are realistic in an applied auction design setting. In a case in point about the IPV model, the IPV model makes this very strong assumption that your signal is only informative about your value and is completely uninformative about the other bidder's values. And should we really expect that to be the case in practice, that you only get information about your own value, but your beliefs about others' values are just coincide with the prior? So all these are a little, these assumptions all seem problematic. And perhaps, you should never try to say something yourself when you can find a eloquent Nobel laureate who already said it better. So I'm just going to read what Bob Wilson wrote on this subject. So game theory has a great advantage in explicitly analyzing the consequences of trading rules that presumably are really common knowledge. It is deficient to the extent that it assumes other features to be common knowledge, such as one player's probability assessment about another's preferences or information. I foresee the progress of game theory as depending on successive reductions in the base of common knowledge required to conduct useful analyses of practical problems. Only by repeated weakening of common knowledge assumptions will the theory approximate reality. So, of course, there are different kinds of robust auction design. You could think about robustness to other features of the model, but in these lectures, we are going to focus on the kind of robust auction design envisioned by Wilson in this quote, namely relaxing common knowledge assumptions about probabilistic assessments. So basically, relaxing assumptions that we make about the form of the bidder's information. Okay. So a natural way that people have interpreted the Wilson critique is that we should be using stronger implementation concepts. So if we use, so Songzi was describing what is often referred to as Bayes-Nash implementation or interim implementation, where the truthful revelation of your private information, or more generally, just your strategy, has to be optimal from an interim perspective when you take an expectation over the actions and information of others. But obviously, that form of incentive compatibility is going to depend on players' beliefs. So Wilson's critique is beseeching us to focus on mechanisms that achieve whatever our goals are as mechanism designers, but regardless of what that detailed structure of beliefs actually is. So in a very extreme form, you could insist that the agent's strategies are optimal for them, regardless of what their higher order beliefs are. Okay, and that's referred to as ex post implementation. So oftentimes the takeaway that people have from the Wilson critique is that we should just use ex post implementation that's independent of the higher order beliefs of the agents. So so often people just start with ex post implementation as, that's the takeaway from the Wilson critique. It's not obvious that ex post implementation is what Wilson had in mind, because he said, you should look for mechanisms that are robust to the beliefs of the agents, but he doesn't say necessarily that it has to be ex post implementable. So a natural question to investigate is whether the Wilson critique, somewhat more broadly interpreted, will lead you to ex post implementation as a solution concept. So that's the avenue investigated by this important paper of Bergemann-Morris that I'm going to exposit next. And again, this paper is written at a somewhat more abstract level that goes beyond the auction design context. But after I take you through this paper, then we're going to apply it in the auction design problem, revenue maximization problem, and we'll see what the implications are. Okay, so in this model, there are finitely many agents, and of them, everything is going to be finite. There's a finite set, big theta, of what I'll call payoff type profiles. And importantly, this is assumed to be a product set. So payoff types are profiles of payoff types for each of the players. There's a finite set of outcomes, Y, that could be implemented by the mechanism. And the agents have expected utility preferences over the outcome that gets implemented and this profile of payoff types. And this is just represented by a von Neumann-Morgenstern utility index. The designer's goals, rather than being represented by an objective function that the designer is trying to maximize, this is a more implementation theoretic model where there is a set of acceptable outcomes that the mechanism designer would like to implement. And those are described by this social choice correspondence, which is a function that maps payoff type profiles into subsets, non-empty subsets of outcomes. So the interpretation is that if the payoff type profile is theta, then the mechanism designer wants to implement an outcome in big F of theta, but they're agnostic as to which outcome in big F of theta gets implemented. So Bergemann and Morris specialized to a class of information structures, which is a little more, has additional structure than what I described at the beginning of the lecture. So I'm going to call them known payoff type information structures. They just call it an information structure, I think. Okay, so in this case, in this class of information structures, we still have a set of signals for each of the agents, but now there's a mapping I'll call theta hat that takes a signal of bidder I into a payoff type. And there's a belief function, but now your beliefs about the payoff relevant state are actually summarized by this mapping, theta hat, and all you need is a belief about other signals. Okay, so this corresponds to an extra assumption on the agent's belief hierarchies that player I knows their own payoff type theta I because they know their signal Si, and given their signal Si, they can figure out what their payoff type is from using this function theta hat. And it's only this vector of payoff types that's payoff relevant for the players. So there's no other state hanging around which may or may not be in the join of the player's information that's payoff relevant. The payoff types are exactly everything that's payoff relevant to them. Okay. So that's the basic setup. A couple of special cases. So one is when your player I's preferences only depend on their own payoff type and doesn't depend on others' payoff types. So that corresponds to the private value hypothesis from lecture 1. You know exactly what your own preferences are over outcomes. It doesn't depend on others' information or others' payoff types. In the quasi-linear auction model, one way of embedding the quasi-linear auction model in this framework is to say that the set of outcomes has a product structure, and there's a zero component, and then there's a player I specific component. And the Y0 component is the joint distribution, is the allocation of the good, basically. It's a probability distribution over which of the n bidders gets allocated the good, or 0 if the seller or mechanism chooses to keep the good. And then Yi, the player I specific component, is the transfer. So that could be just any number in R. And then the expected utility preference, the utility index has a special form where, of course, you have to pay your transfer, and then you have utility from the allocation that gets implemented and the vector of payoff types. One last thing that I could mention as a special case, an example of a known payoff type information structure would be the independent private value model, where SI, so this is IPV, that's when SI is equal to V, the set of possible values, and theta hat of SI is just equal to SI, so the identity mapping. Your signal is exactly equal to your value. And then you could specify these beliefs, say, according to a common prior as independent prior as in the IPV model, if you so chose. Let's see like this. Pi I is equal to F minus I. That would be the IPV model. All right. So here are two different ways that you could try to implement an outcome. So in this paper, we're focusing on direct mechanisms. So an implicit premise there is that the mechanism designer has access to a very rich set of mechanisms, and also that the mechanism designer can choose the equilibrium that is going to be played by the agents. So those are kind of the two critical assumptions for a revelation principle to be valid, and for it to be without loss to restrict attention to direct mechanisms. So with those implicit assumptions in hand, well, which are now explicit assumptions, I suppose, because I just stated them, we're going to focus on implementation with direct mechanisms. Okay, so if I fix one of these known payoff type information structures, then a direct mechanism on that information structure is a function f that maps signal profiles into outcomes. And we'll say that direct mechanism is interim incentive compatible if for every player and for every pair of signals, SI and SI prime, the expected utility of bit or I when they have signal SI, which is this expression on the top, and report SI, is greater than their expected utility if they have type SI and report SI prime to the mechanism. So, this part is what's affecting the payoff types, and that's the same regardless of what you report to the mechanism. This one is the same regardless of what you report to the mechanism as agent I, because that's just determining your beliefs. But this is the type that agent I reports to the mechanism and affects the outcome that gets implemented. Important thing here is that agent I only has to find truthful reporting to be optimal and expectation across the types of the other agents. Okay, and we'll say that the social choice correspondence F is interim implementable on this information structure if there exists an interim incentive compatible mechanism, direct mechanism, such that the implemented outcome is always in the set of acceptable outcomes for the given payoff type. A stronger implementation concept is ex post incentive compatibility, ex post implementation. So how does that work? Well, whereas up here we had a mechanism map signal profiles into outcomes, so this depended on the particular information structure. With ex post implementation, the mechanism is going to map payoff type profiles into outcomes. And this direct mechanism is ex post incentive compatible if basically truthful reporting is optimal in the complete information game, where all of the agents know the entire vector of payoff types. And if you know the entire vector of payoff types, reporting your true payoff type is optimal, is better than misreporting any other payoff type. And the social choice correspondence is ex post implementable if there exists a direct mechanism that is ex post incentive compatible and the implemented outcome, or the outcome that results from that mechanism, is in the social choice correspondence for every vector of payoff types. A brief aside on ex post implementation and dominant strategy implementation. So the F would be dominant strategy incentive compatible if this condition is satisfied. So what is the key difference between ex post implementation and dominant strategy implementation? Well, down here, we're conditioning on the true payoff types and on the fact that others have truthfully reported their payoff types to the mechanism. Okay, so this is saying that even if you had complete information of the payoff types, truthful reporting is optimal as long as others are truthfully reporting. Dominant strategy incentive compatibility further requires that truthful reporting is optimal even if others misreport. Okay, so it clearly dominant strategy incentive compatibility implies ex post incentive compatibility, but in general it's weaker, and they coincide in the special case of private values, because then basically theta minus I doesn't enter into your preferences except through the outcome that gets implemented. So this would be equal to, say, ui of f of theta I prime, theta minus I prime, and then theta I, theta minus I prime, because what you plug in here doesn't matter for player I's preferences. Okay, so for consistency, even when we specialize to the case of private values, I'm going to use the term ex post incentive compatible rather than dominant strategy incentive compatible, even though in a lot of the literature on this subject, in the private value context, you will see them referred to dominant strategy mechanisms. Okay, so here is a basic result and kind of the reason why people often equate the Wilson doctrine with ex post implementation. If F is ex post implementable, then it is implementable, interim implementable on all known payoff type information structures. Okay, and there's a very easy argument for this. Suppose F is ex post implementable, say by this function F that maps theta into outcomes Y. Well, then F is implementable on any information structure by the direct mechanism where essentially when the signal profile is S, you just have everyone report theta hat of S and then run this mechanism. Okay, and it's very straightforward to check that this is going to be interim incentive compatible. So suppose we have the social choice function F, and we want to implement it regardless of the details of the player's higher order beliefs. Of course, one way to do that, if F was ex post implementable, then you could do it, as we showed before on the previous slide, just by picking any ex post incentive compatible direct mechanism. But it's conceivable that there are social choice functions that can be implemented on all known payoff type information structures, even though you can't do it with an ex post incentive compatible mechanism. Okay, so so the question that we want to answer now: does the Wilson doctrine, more broadly interpreted, inevitably lead us to ex post implementation, or are there other weaker solution concepts that you could use that would still achieve F regardless of the details of higher order beliefs? So the answer is going to be a qualified yes, that the Wilson doctrine leads to ex post implementation, but only if we put extra assumptions on the environment. And those assumptions are going to be general enough to include the auction design framework that we were talking about in lecture 1. Okay, so let me describe that condition. So we'll say that this environment consisting of the payoff type profiles, the outcomes, preferences, and the social choice correspondence, that's going to be separable if, first of all, we can decompose the outcome into this Y0 component and then player-specific components. Player I's preferences depend on the 0 coordinate and their specific coordinate, but not on the other player's coordinate. So that's sort of like the quasi-linear model where a player's preferences depends on the allocation and their transfer, but not directly on others' transfers. And the last condition is that the social choice correspondence has a special form. So basically, there's only one acceptable outcome for the 0 component, for the 0th component, when as a function of the payoff type profile. There may be lots of acceptable alternatives for the player I specific coordinate, but there's a product structure. So the set of acceptable outcomes overall is just the product of this one acceptable outcome on the 0 coordinate and the product of all of the player specific components. So, a special case would be, we really want to implement a specific allocation, but we're agnostic as to which transfers we use to do it. And there's no interaction between the designer's preferences over the transfers that are used for player I and the transfers that are used for player J. Okay, so this is a substantive assumption on the environment, but we're going to run with it. And this is stuff that I've already said. Okay. It's sort of makes sense. So yeah, let me not say anything more about that. Okay, here's the proposition. If the environment is separable, and F is implementable on all known payoff type information structures, then F is ex post implementable. So when you specialize to separable environments, Wilson doctrine is equivalent to ex post implementation. That's the point of this proposition. Okay, so why is this true? So I'm not going to take you through any heavy duty proofs, but I'm going to give you a sketch of why this is true. So we're trying to implement this F, okay? And we've got to construct an ex post mechanism that implements it using the fact that it's interim implementable on all type spaces, all KPT type spaces. So we're going to build up that ex post implementing mechanism piece by piece by looking at carefully chosen information structures, KPT information structures. So here is how we're going to figure out. So by the way, if it is ex post implementable, then it's going to be implementable with a direct mechanism that's of the form F0 times product over all i's, Fi, where this F0 is already given to us by the social choice correspondence because of the assumption of the special structure. So really the only things that we have to find are these Fi's, the outcome that's going to be implemented for each individual player as a function of their payoff type. Okay, so look at the special information structure where it's only player I who has private information about their payoff type. All of the other players are known to have particular payoff types, and they have no information, okay, or they have degenerate information. Okay. So separability and the fact that F is interim implementable means that there exists this component of an interim implementing mechanism that makes it optimal for player I to report their type truthfully when others' types are theta minus I. So that's all this line is saying, is that if the outcome of the ith coordinate is given by this GI function, and the 0th coordinate of the outcome is given by the F0 function, then it's optimal for player I to report, even when they know that others' types are theta minus I. Okay. So from separability, we know that there are no joint restrictions on the player-specific components of the outcome. So we could piece these GI functions together to construct a direct mechanism that is ex post incentive compatible. And we do that by just taking the direct mechanism F prime of theta to, first of all, implement what we know it has to implement on the 0th coordinate. And in the ith coordinate, implement this GI theta minus I outcome that we got from this line. And it's easy to show just using this line right here that this direct mechanism that we've defined in this way is ex post incentive compatible. Easy peasy. You can't get rid of the separability hypothesis that easily. So I'm not going to go into this detail in this example in too much detail, but this is an example of a non-separable environment where interim implementability on all KPT information structures is not equivalent to ex post implementation. So, so here there are two players. Each player has two types, and there are three outcomes. And what I've written here are the ordered pairs of players' utility indices for each outcome that could be implemented and for each pair of types that they could have. Okay, so the social choice correspondence that we want to implement is, it doesn't depend on player two's type at all. It's just if player one's type is theta 1, we want to implement either A or B. So we want to be in this region. And if player one's type is theta 1 prime, we want to implement C. Okay. Now this outcome is easy to interim implement. And you can do it by just telling player one, they're the dictator. You get to pick which outcome. And, A is better. A is much better than C. C gives a payoff of 0 to player 1, whereas A gives a payoff of 1 when they have type theta 1. So, it's easy for player 1 to just pick, sorry, I should say that one of these two has a payoff of 1. A or B has a payoff of 1. So, whatever the beliefs are that player 1 has, they'll be better off either picking A or B when their type is theta 1. And by a similar logic, when player 1's type is theta 1 prime, they get a payoff of 0 from either A or B. They get a payoff of 1 from C. So it's obviously going to be optimal for theta 1 prime to select alternative C. Okay, so that's an easy way to implement this social choice correspondence but it's an interim implementation in the sense that it's going to depend on player one's beliefs. Whether player one, when they're type theta one, thinks theta two or theta two prime is more likely is going to affect whether they think A or B is the alternative that's better than C. But you can show that actually this social choice correspondence is not ex post implementable, because basically no matter if you implement it ex post, then at each of these profiles, you're either going to have to pick A or B. And whatever you're picking, I could select the beliefs of player one in such a way that they would actually prefer the C alternative if they have the option by misreporting as theta one prime. Okay, but that's not hugely relevant to us right now, because we are chiefly concerned with the auction design problem, and the auction design problem can often be cast as a separable environment. Okay, so what we're going to do next is, okay, so Wilson doctrine in separable environments can be interpreted to mean just use ex post implementation. So what does that imply? Let's look at ex post implementation in the standard auction setup that Sangzu was describing in lecture one. And I'm going to use even exactly the same notation, that there's a finite grid of values, and the values are evenly spaced, and gamma is the gap between the values. So we're going to continue to assume private values. So each bidder knows their own value, but they may have, the possibility of rich information is leading us to use, and the desire for implementation of this outcome independent of the player's beliefs is going to lead us to use ex post implementation as the implementation concept. So the ex post incentive constraints take this form, that for any profile of the true values of the bidders, it's better for bidder I to report their true value, VI, which is in here somewhere, versus reporting a VI prime. Okay. It is standard to also require that the bidders actually want to participate in the mechanism. And in the spirit of ex post implementation, we're going to impose an ex post participation constraint that, conditional on the value profile, bidder I's surplus from the mechanism is non-negative. Okay. So profit maximization with ex post implementation. What are the mechanisms that maximize profit for the seller ex post? So of course, in order to talk about expected profit or expected revenue for the seller, we have to also specify beliefs for the seller. What do they think is the probability distribution over the bidder's values? So we're going to denote that by F. Importantly, this F is not the same F that was used in lecture one. In lecture one, F was both representing the distribution of values from the seller's perspective, but also it was a common prior for the agent's beliefs, and it was being used in that way. Here, we're only using it in that first sense and not in the second sense. Okay, so with that caveat out of the way, here's the revenue maximization problem. Maximize the expectation of the sum of the transfers of the bidders, subject to basic feasibility restrictions on the allocation, that you can't allocate the good more than 100% of the time, and then these ex post participation constraints and the ex post incentive constraints. An interesting side note is that, it's actually very important in this problem that we use an ex post participation constraint rather than an interim participation constraint. The Kramer and McLean construction, given sufficient independence assumptions on beliefs, you can extract all of the surplus even with ex post incentive constraints, as long as the participation constraint is interim. So it's crucially important that we're setting up the problem with this constraint rather than an interim constraint. All right. So the analysis of this model of the ex post implementation problem is going to proceed very much the same way as in the independent signal case. Okay, so we're going to derive an upper bound on expected revenue using in terms of virtual values. And I'm going to do it in much the same way as Sangzu did it in lecture one, using Lagrange multipliers. Okay, so Sangzu showed that with a judicious choice of Lagrange multipliers, you can reformulate the Lagrangian as just maximizing the virtual value. So here's another way of seeing how that would work. Okay, so we're going to pick Lagrange multipliers on the local downward IC constraints, and we'll call those alphas for now, TBD. And we're going to take this weighted sum and then add it to the objective, okay, to try to get an expression that looks like the virtual value, okay? And in this formula, I just want you to interpret this QI of V0, which is really outside of the range of values, as 0, in which case the lowest of these constraints with m equals 1 is actually the participation constraint. Okay. So you could sum this by parts and get this expression down here. Okay. And the idea, another way of saying what Songs has said in the last lecture, is to choose alpha so that the transfers drop out. We want the transfers to drop out so that we end up with that virtual value formula. So we need to pick alpha so that when we add this to the revenue formula, it'll all cancel, okay? And the way to do that is by picking this form for alpha. If you pick this functional form for alpha, then this expression will exactly reduce to f of v, okay? And that's what we're gonna do. So if you do it, then this is the formula that, okay, so this would be the weighted sum, and this is the part that's going to cancel with the term in expected revenue. And this part that you're left with is a generalized virtual value, a little different from the virtual value that we had before, because now it actually also depends on the values of the other bidders. Okay, so it's a subtle difference, but an important one. Okay, so this sum is non-negative because we have non-negative multipliers, and if we choose the mechanism to be ex post incentive compatible and individually rational. So if we add all of these terms for every I and in VI, just for every I to the objective, then we'll get a bound that expected revenue is less than or equal to the expectation of the virtual value of the bidder who gets allocated the bid. Easy peasy. F, we're going to call it regular if this phi is non-decreasing. And, you could describe at more generality, without strong assumptions on phi, what the optimal mechanism, what the optimal solution is to this program. But for the purpose of this lecture, it is sufficient to explore this simple case, the regular case, where phi is non-decreasing in VI. And in this case, the upper bound is maximized by a mechanism that allocates the good to a bidder with the highest phi of v. And it's straightforward to show that mechanism, that would be the allocation that maximizes the upper bound. And in the regular, of course, this is always the allocation that maximizes the upper bound, is just to allocate the good to whoever has the highest phi of v. The special thing about regularity is that allocation that maximizes the upper bound is also implementable. You can show that there's a way to choose transfers so that all of the ex post incentive constraints are satisfied, which basically comes down to the fact that in the regular case, the allocation that solves this is going to be such that QI of V is non-decreasing in VI. That's the critical property for every V minus I. Okay. Moreover, in this regular case, the alpha I of V that we described on the previous slide must be the optimal Lagrange multiplier, because when you use it, it gives you the correct upper bound on surplus. And the other multipliers are all 0. Okay. So, as we discussed, as Songs had discussed in the first lecture, when there is this analysis, by the way, was true regardless of what F is. F could be correlated in essentially an arbitrary way. And if you were using interim implementation, and if you knew something about the bidder's beliefs, then you could generally do better, sometimes a lot better, with interim implementation than with ex post implementation, such as by using Kramer and McLean mechanisms. So, as we've been saying all along, one foundation for these ex post mechanisms is that we want the outcome to be implemented on all known payoff type information structures. Of course, if the goal is revenue maximization, you might ask yourself, well, why do I care whether the same exact outcome is implemented on all information structures? What I really care about is what is revenue, If revenue is good on all information structures, then why do I care if the particular outcome that's implemented is changing? Okay, so this suggests a different criterion that we like a mechanism, not if it always implements the same outcome, but if it always generates a good amount of revenue. Okay. Now, of course, if you have an ex post incentive compatible mechanism, one option is to just run that, and it will always generate the same amount of revenue that we just characterized, which we'll call pi star. Okay, so a natural question is there any other mechanism that uniformly does better in terms of generating higher revenue on all type spaces than this ex post mechanism? And in this regular case, the answer is no. And that's a result due to Chung-Ely 2007. Okay, so how does this result work? So what they do is they show that for any mechanism that you could pick, there is an information structure, KPT information structure, such that expected revenue in that mechanism is no greater than pi star. Okay. In fact, they construct an information structure where pi star is optimal revenue. And that's the information structure that proves that it's impossible for the seller to do uniformly better. And so I'm going to describe to you this result and the worst case information structure that Chung and Ely construct. Okay, so they construct this worst case information structure. The optimal ex post mechanism that we just described and this information structure, there's sort of a saddle point for a max-min problem where the seller is trying to maximize revenue over direct mechanisms in some, say in the universal type space, and nature is trying to minimize revenue by choosing a prior over the universal type space that's consistent with the seller's beliefs about the value. And basically, this mechanism is going to maximize revenue on this information structure, and there's, anyway, it's a saddle point. We'll subsequently return in the next lectures to this notion of a saddle point in the robust auction design problem. So that's why I'm flagging it at this stage in the exposition. Okay, so in this worst case belief structure, worst case information structure, of course, we could pick the set of signals to be whatever we want in an information structure. But it turns out simple information structures suffice, where the set of signals is just equal to the set of values. Okay, so each bidder is going to get a signal which is equal to their value. And so the only component that remains to be determined is the beliefs. What are the right beliefs to specify so that pi star is maximum revenue in the interim revenue maximization problem? Okay, so this is what that program looks like. Again, we're maximizing expected revenue. Again, we have some feasibility restrictions on the allocation. And we have participation constraints and incentive compatibility constraints. The key difference, of course, is that now this isn't an ex post constraint, this is an interim constraint where we're using these beliefs pi I. And we're using the beliefs down here as well. Okay, so the name of the game is to pick pi I so that the value of this program is pi star. And in fact, you can derive the pi star that does that from the Lagrange multipliers that we described previously. So how does that work? From the regularity hypothesis, we concluded that only local downward IC and the participation constraint for the lowest type are binding, and the optimal multiplier is this form. It's this upward sum, holding fixed V minus I. Okay, so basic fact about linear programs. If you have a linear program, and then the value of that program would remain the same if you take a subset of the constraints and you replace them by a weighted sum of those constraints where the weights are proportional are positively proportional to the Lagrange multipliers. Okay, so what that means is that the value of the program P, the revenue maximization over ex post incentive compatible mechanisms, the value of that program remains the same if we replace the ex post IC constraints with an interim IC constraint, as long as the weights that we use are proportional to the Lagrange multipliers. Okay, so this C is a constant that depends on bidder I's value, but doesn't depend on V minus I, which is indexing the constraints that we're aggregating. Okay, so let me suggest that we take that constant to be 1 over the sum of the Lagrange multipliers over V minus I. Okay, then this, and define pi star to just be this product, to be this weight. then this is a belief, right? If you sum these over v minus I, it'll sum to 1, okay? So that aggregated incentive constraint is just a Bayesian interim local downward IC constraint for these beliefs pi star. And you can do exactly the same thing for the participation constraint of the lowest type and aggregate up those participation constraints into a Bayesian participation constraint. Finally, all of the other constraints in the program P were not binding. Their Lagrange multipliers were 0. You can aggregate them up however you want, and it's not going to change the value, or drop them, and it's not going to change the value of the program P. So just for the hell of it, why not aggregate them up with weights pi star? And if you do that, then you end up with an interim revenue maximization problem that has the same value as P. So just to wrap up the lecture with some concluding remarks, the Chung-Ely result is incredibly beautiful, and it further justifies ex post implementation in private value auctions. But it still relies on a somewhat strong regularity assumption and the hypothesis of private values. There are some papers that have been extending this theory beyond the private value case and the regular case. So you could look at these references if you're interested in pursuing that further. All of these results rely on a failure of the common prior assumption. So in particular, these beliefs that we've described over here, these are not consistent with a common prior, okay? Which is important to note. And also Chung-Ely show by example that relaxing regularity and imposing the common prior assumption will both break the result, which is not too surprising because, of course, the problem is only going to have the same value. The interim implementation problem is going to have the same value only if the beliefs end up being proportional to the Lagrange multipliers in the ex post problem, and those are pinned down. We don't have any flexibility about what those multipliers should be. Final thought on ex post implementation, or more generally implementation on all type spaces versus max min. Bergemann and Morris 2005 give us this nice characterization of when ex post implementation captures this desire for robustness to information that's embodied in the Wilson critique. And Chung and Ely give us an alternative foundation in terms of max min. Both of those are a foundation for ex post implementation in their respective environments. A problem with ex post implementation is that in general, there are not many social choice functions that are ex post implementable. So Gilles, Meyer-Tervain, Moldovanu, and Zame showed that generically, even in an interdependent value but quasi-linear environment, generically the only ex post implementable social choice functions are constant. So they're just independent of the agent's reports, which is not a terribly useful class. So that suggests a limitation to using ex post implementation in richer environments. But you could still use the max min criterion. It just might not lead you to ex post implementation. Okay, so this suggests that maybe max min is more fruitful than ex post implementation as we go forward. Okay, final thought, especially because the audience at this tutorial is likely to consist of a mix of people with a computer science background and an economics background. I want to speak to the sort of difference between the robustness perspective in this field, or this area of mechanism design, versus other kinds of robustness, say those that are pursued in algorithmic game theory and algorithmic mechanism design. So in algorithmic mechanism design, often the style of modeling is to make simplifying assumptions about the form of information, say to look at independent private values or private values, and look for robustness in a broad sense to the fundamentals, to the distribution of the value itself or the value in a prior free model. And then the evaluation criterion generally takes the form of constant factor approximation. So the difference here is, we may be willing actually to fix a prior over the values. Of course, the solution of the ex post mechanism design problem that we reviewed several slides ago depends on F, depends on the prior. Whereas, while we instead look for robustness with respect to the information and the beliefs. Although I should, as I said at the beginning of the lecture, there are other notions of robustness that are sometimes studied, but in these lectures, we're focusing on beliefs. Also, rather than say using constant factor approximation, we're using more implementation theoretic or optimization based criteria, so revenue maximization. So there are obvious areas of overlap to be explored between these methodologies. In particular, you could combine the study of robustness to information with the study of robustness with respect to fundamentals. One could also look for mechanisms that provide good constant factor approximations regardless of the information that the agents have, in addition to regardless of the distribution of fundamentals. That's where I'll stop for now, and we'll continue tomorrow with lecture 3.